There we go. Okay, good morning again. We're at the lab here. Today's lab is on oscillations, and we're also going to do a damped harmonic oscillator. Now, this is a bit more doing the damped harmonic oscillator than I'm holding you responsible for the course in general in terms of material, but you're still responsible for this lab because you're being walked through it in the lab itself. And I want you to look, the point is to look at how you need to sometimes look at the characteristics of your data and logarithmic functions. Now, we hear about logarithmic functions, and logs can be in many different bases, okay? You hear the word log, that's a common one on a calculator. If I pull up my calculator here, let me go ahead and, give me 1 second here. Go ahead and share screen here. Okay, I'm gonna share screen. Just extra information for you to help you through things. If you look at my calculator here, you'll see I have an ln and I have a log underscore 10. Well, logs depend on a base system, okay? Log with a little underscore 10 is log base 10. ln is equal to log with an e, and that's log base e, just the exponential log. Okay, now logs are a neat function. You know, log of value a to the x is equal to x log a. And I'm doing 10, a value of 10 to the x. Okay, now if I do ln e to the x, that's x ln e, and log of e is 1. Okay, so if I do, for instance, so if I wanted to have the ln e to the power of 12, that just equals 12. If I do, so here's 12 e to the x, which is 162,754. But if I take the natural log of that, I just get 12 back. Same if I do log of 10 to the 12th, that's equal to log base 10 of 10 and times 12 log base 10 of 10. Okay, but log base 10 of 10 is just equal to 1. So this is just equal to 12. So if I do 1 exponent 12, which is the same as 10 to the 12, and I take the log of that, I get 12 back. So the log and numbers raised to a power return the log of a value. Now, why do I bother to spend this time through here? Well, depending on your type of function that you have, okay, I can have curves like this. And if I have a general idea on the shape of my curve, I might apply that function to the all the numbers or the inverse of the function. For instance, if I had a curve that was, say, x squared, and I get a bunch of data points, and I have a curve that goes as x squared. Well, fitting the data to that point might seem a little bit more difficult. But if I take every one of my points, so if I have, a set of points, and this is say, X and Y, and I was taking data and I said, oh, that looks like a quadratic, but it's kind of hard to fit a straight line to that. Well, if I had X and Y and it was perfect, I would just have 1, 1, 2, 4, 3, 9, 4, 16, 5, 25. But I might have something that's close to a quadratic and I want to kind of understand it a little bit better. Or I might have a function that was y equals, some factor mx squared plus b. Well, I want to get rid of the x, so I might take a square root of things to get that slope. And we're going to see that you can do that because if I then plotted my data, but I took the square root of all my data, I would then be plotting a straight line. So we're going to see doing that in today's lab. So let's move on to today's lab. That's what I want you to get out of today's lab. Okay, so let's go let me pull up today's lab. That the part of today's lab that has damped motion in it. I'm going to pull up the lab. Now we have already been introduced to our harmonic motion. In our very first lab that we did some of this. Okay, so we're going to do with and without damping. So we're going to pull up our labs. We have our basic background equations. Let's not forget our basic background equations. We had them introduced in today's lecture. Okay, we've had them introduced in the past where we talked about frequency, period, and angular frequency. So frequency is 1 over t, or t is 1 over f. This is the frequency and the period of oscillations. Our angular frequency, which we always have to do everything in angular frequency, we want it in radians per second, is 2 pi f. F is revolutions per second, or that's 2 pi over t, where t is the period. For an ideal spring, we have a restoring force. F of x is minus kx. That's just Tooke's law. The acceleration. Well, here I've written down a little bit of calculus. You don't need to know what this means here. This is just a little bit of calculus. All right. But f of x, a sub x is f sub x over n, m, which is minus kx over m. It turns out that's equal to the second derivative of x with respect to time. That's a very convenient thing to know because that sets up what's called a differential equation. So I've written it in here as extra information. You're not expected to do calculus or solving differential equations. All we need to know is AX is minus Km over time. And as we've shown before, our angular frequency omega is just the square root of K over M. So AX is minus omega squared x. Now, we could have an amplitude. This is all if, okay. Now, our amplitude has, x has our amplitude in it is also when we do the full displacement in a harmonic motion or simple harmonic motion. So f, which is omega over 2 pi, is 1 over 2 pi root k over m, or t is equal to 2 pi times the square root of m over k. All very convenient things to have. Okay. Now, displacement in a simple harmonic oscillator, as we already showed, is A. It has an amplitude cosine of omega t, where omega is the angular frequency, times time, plus some starting phase angle. So A is the maximum amplitude and phi is the starting phase angle. So x0, some initial position, is equal to A cosine phi. And we can get our two equations and our two unknowns. And of course, we also had our velocity in there. We also know that our total mechanical energy is 1/2 mv sub x squared plus 1/2 kx squared. And that has to equal to 1/2 k a squared, because we know that when the displacement is at its maximum, the velocity is 0. So this contributes 0, and this is 1/2 kx squared, and this is the case when we have no damping. If we have simple harmonic motion with damping, it's a much more complicated looking equation. Both the frequency is affected and the amplitude is affected with time. So often, damping is either intentionally added or some level is unavoidable in oscillating systems. You have air friction. If I start a pendulum in motion going back and forth, just realize my screen is off here. If I have a pendulum going back and forth, okay, you guys need to remind me when my screen's off. I don't know why it's defaulting to that, okay? It's going back and forth. You know that if you start a pendulum going back and forth, it's eventually going to dampen out and stop swinging back and forth. And in fact, it doesn't take very long to do that typically, because air friction in your fixture that's holding it, other ways it removes energy by the bending of your structure, transferring all sorts of energy. There's all sorts of ways that you can use it. Those are unintentional damping. Okay. If we have light damping, okay, we can derive an expression for the position of an oscillating system with light damping as x. Now this is a much more complicated looking formula. X is equal to e raised to the power of minus b over 2m times t, okay, cosine omega prime t plus phi, and b is a damping factor. Omega prime is now going to be equal to the square root of k over m minus b squared over 4m squared. I'm just giving you these formulas. More complex algebra, in the end, you're really into algebra, but you're also going to be taking the natural log of some data. You're going to measure the data, you're actually going to make the measurements, and you're going to take the natural log of this data. So we're going to start with the simulation. Which I have now opened up right here. Okay, so we've downloaded it. And we can start with our intro box. And note there's no damping in the intro box. Drag the ruler and time out. This is just like we did before. Click on the natural length and equilibrium position boxes. Okay, so we're going to click on the natural length and equilibrium position boxes. Okay, we went ahead in that. And use our mouse and put the 100-gram mass on each spring. We got 1 and 2. And we're going to click pause and pause. And you should see something similar to this. So this shows the natural length, it shows the equilibrium position. Okay, these boxes stop the oscillation, all the typical things. Here's our position of our slider. We're going to call this position 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are 10 positions starting with 1 on the left. I think I started with 1 on the left. We have play buttons, we can run in slow motion, and we can move in increments of 0.01 seconds. So we're going to run this spring constant as small as possible, and this spring constant as large as possible. We're going to measure the distance from the natural length to the equilibrium position. Okay, now we did this before. And we're going to attach the 250 gram mass here. So we've got the 100 gram mass on this one as small as possible, and the 250 gram here. Now, if I went and stopped this, and I put the 250 gram here, you know, we end up with things off the screen. We could actually measure this if we wanted to, but we'll stick with the 250 and the 100. Okay. And we're going to use equation 3 above to determine the spring's constant when set to the small and the largest value, when we're set to the smallest value and the largest value. So what's my equation 3 above? Equation 3 is F equals minus KX. Okay. Hooke's law. What's the force in this case? All of you better be able to give me the right answer on this.
The 250 grams?
That's part of the force. What's the force? So here's my 250 grams. That's part of it. mg. Force downward equals mg. So the force upward is kx. We know what mg is. Okay. We have x is in, you know, the negative direction, and we can measure it. We can take our ruler and measure it. It looks like about 20 centimeters. So we have mg down, which is 250 grams or 0.25 kilograms times 9.8 meters per second squared equals k times 0.2 meters. So now I can calculate k. So that's the spring constant, the largest in the smallest and largest position. Now, if you go back to your lab 1, you should have a table of spring constants. And we're just going to get close on this one. The best way to measure the spring constant would be to measure 100 cycles, the time for 100 cycles, and use that omega is equal to the square root of k over m, or 2 pi, the period equals 2 pi times the square root of m over k, just like we did in lab 1. Okay, so for slider position 1, so you have your k small and k large. Okay, here's our spring constant bar. You're going to calibrate this knob to a spring constant. So we go to this one over here. If you can choose what mass to use, the bigger the mass, the more resolution you have, because my least count of this ruler. So if I put this one on and stop it, I have at position 1, I have a mass of 250 grams. So I'd go over here and I'll try to get this on here. Let's see if I can see if I can figure out how to add text here. To me. So 0.25, 0 kilograms. My displacement is 0.82 meters, or I could do 820 millimeters. You can just do meters, choose your, this has displacement in millimeters, it wrote here. That'd be 800, that would be 820 millimeters. And my spring constant in newtons per meter is 0.25. So force is 0.25 times 9.8 divided by 0.82. And it's 2.99 newtons per meter. Probably 3. I move this to position 2. And stop it. Well, this is about 61. And I have it in meters. Okay, I go back here. 0.25. 0.25, 9.8 times, and 0.61 divide. That's 4.02. Oops. So you're calibrating this. If I go to position 2, 3, 4, 5, 6, 7. 7 looks to be about 30. I can't quite read that. Looks like about 32. Well, now if I do I get 7.65. Well, now you start seeing that this is
Teacher, that one
Yeah.
is 32. It's no 29.
you're right. Thank you. It's not 32, it's 27. And I get 9. So
9.8.
2, 3, 4, 5, 6, 7. What's that?
The spring constant for number 7, the one that we're just calculating, it calculates to 9.07.
You're gonna need to redo these yourself.
Yeah, but not like for like the example that we're doing, just so I know that the calculation like that, I am understanding how to calculate them.
Okay, so I do 0.25, yes. 9.8 times
Mhm.
and 0.27 divide, because F equals K, and I get 9.07,
Okay.
which is what I kind of expect. So this side comes out as 9.07. Oh, 9.07, let's write it here. 9.07. Okay, you go through and you calculate these all the way from 1 to 10. You should have a good idea as to where they're going from. They're going about 1 per spring constant and all of that, because it's going to be 10, 11, 12. This started at 3 with position 1. You should be getting a guess at how this is moving and what you should be getting. Okay, but go through, make the measurement, make the calculation. We're calibrating our knob. I can give you a knob that has the values 0 through 10 on it, but you don't know if it's 0 through 10 volts, 0 through 10 millivolts, 0 through 10 newtons, 0 through 10 millinewtons, 0 through 5 newtons, 0 through 5 millinewtons, 0 through 5 volts. You have to calibrate something that just has an arbitrary dial on it. This has an arbitrary dial. It says small and large. That's all it says, with some notches in between. You need to calibrate each of those notches. That's the act of calibrating your instrumentation. Okay, it's one of and your measurement system. So I have a variable spring constant that has a knob on it. Okay, that knob has absolute positions. I need to calibrate that knob. That's your job in here, is to do calibration. That is a common thing to need to do in a laboratory environment.
Got it. For 4.2 exercise 1, when we're finding the spring constant for the large and the small one, we do the same formula as for the table, correct?
Yes,
Okay,
you just find the spring constants for each one of these positions. You're calibrating your lab.
got it. Thank you.
Okay, now we can do this the same way for each of these masses. You can do a number of cycles. Okay, on this one, I asked you to go to, we're now going to switch to lab. Now, I'm pulling up the same one. Okay, in this lab here, this says 100 grams. Okay, we're going to switch to the lab. We can add the 100 gram and then click the stop button. Now we're going to do this. We're going to measure the spring constant a different way. You can go back to the lab that we did, set your damping to none for this. Okay, you can go back to the lab you did for number 1, our very first lab where we did this. Okay, but we're doing it again here, and do at least 10 cycles. Now note here, you can adjust your mass from 50 to 300 grams. And you can just, okay, so you're going to do 50, 100, 200, and 250. So you see the difference. This is showing kinetic energy, potential energy, gravity, potential energy, elastic, E total, and E thermal. Okay. Now we're going to trash all these because we're not having any damping right now. Okay. If I want to put on my 300 gram mass, pull this guy out. This is your clock. I ask you to show here. Okay. We're going to set the simulation to slow. Makes it easier to count. We've set this to 0. set our spring constant to position 4. That's 1, 2, 3, 4. Now we are assuming that our spring constant here is the same, but we're going to validate that. We're going to validate the position 4 is the same. Okay. We're going to turn on our displacement, our mass equilibrium line, okay, and a movable line. We're going to take this, we're going to move it to about 40 centimeters below. Okay, we may not be able to get quite that much, or I may need to make this bigger. That won't work. So sometimes you can't even put this at a full 40 below. So I'm going to set it at 50 here. And I'm just going to subtract 50. So looks like I can only get it to about 30 below for the 300 kilogram or 300 gram. But if I do the 100, I can get it to 40 below. Here's my 200 right here. So I'll do 200 and 40 below. Okay. So now I put this 0. Sometimes, see, I sometimes you won't be able to drag it all the way down. So you'll have to know that I would go, say, from 10 to 50 is 40. So there's about 50 below. Now, it really doesn't matter how far I pull it, which we've already seen. Now, let's get to 200, even. Okay, move below the mass equilibrium line. Drag the mass, so the movable line intersects the mass in the center of the mass. So I'm going to hit stop. And there's my 40 below. Now that distance here doesn't matter all that much. And it's paused. Okay, run the simulation until just before 10 cycles get complete. Now remember, a cycle is up and back down. And it's going to be right when it crosses in around 0. So I'm going to start my stopwatch. Notice it's not counting because I haven't hit go. We go up 1. So here's 1 full cycle. And we can do a period trace. Here's 2 full cycles. There's 3. Get a little bored, you can hit normal. Here's 4, 5, 6, 7, 8, back to slow. There's 9. And here comes 10. Now I'm going to pause it about here. And I can move this with this guy, small increments. Notice it's 11.33, 34, 11.34, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now we'll do it back up. So 11.48. So 11.48 is the time for 10 periods in a 200 gram mass. So we did 10 cycles. Time for 10 cycles was 11.48 seconds. So my period is 1.148. Okay, if 11.48 for 10 cycles, divide it by 10, and you get 1.148 for a single cycle. My frequency is just 1 over that. So 1.148, and it inverts that. That's 0.8711. And anyway,
Sorry, what do you mean by invert 1.148?
frequency is 1 over the period. So to invert it is the invert is 1 over.
Oh, okay, thank you.
So it's just 1 over X, and I have a 1 over X key here. And my angular frequency is 2 pi times my frequency. And that's not correct. $5.4733. Okay, so that's my angular frequency. That was all at 200. Okay, for each mass, verify the above formula that T period is equal to 2 pi m over K. Or to do that, we're going to do, here we had a period of 1.148 equals 2 pi, this is a question mark here, 2 pi square root of m, which was 0.20, and my K for position 4, I'm going to say is about 6. So I'm just verifying this. So 0.2, we put it in position 4. Your calibration table should tell you that that is 6 newtons per meter at 4, at position 4. Hopefully it does. Take the square root of that. And this side here is 1.1147. Boy, those numbers are awful close, aren't they? So 147. 1.147 versus 1.148. Numbers seem awful close to me. So Rhea validated that. Okay, you're going to verify your calibration table. Okay, at least for that position 4. So do the values agree for the period agree with the values calculated from above? I certainly hope so. Now we have a planet X. You're going to determine the gravity for planet X with 2 unknown masses. You're going to measure the number of cycles, the time for the number of cycles, the period, the figure, the frequency, the angular frequency. You're taking your spring along. It's a calibrated spring. You have a spring constant. You're going to measure the displacement. Okay, from that displacement, okay, you can get a calculated mass and the gravity of the planet, okay? But you have 2 unknown masses. You have to use the unknown masses and the unknown planet X. We don't know what it is. And we have to use an unknown mass. But what do you know? You know T equals 2 pi square root of m over k, or omega is equal to the square root of k over m. I don't care which way you do it. So what do you know from here?
Move the lab out the way.
No, you have to just listen to me and hear my words. I refuse. Okay, no, I didn't really refuse. So you've calculated the angular frequency. Okay, let's just stick with this one for right now. So this one I can write. Square root of m over k is equal to t over 2 pi. Or m over k is equal to t squared over 4 pi squared. Or m is equal to t squared k over 4 pi squared. So I don't care if you take a calibrated spring along, a simple calibrated spring along to any planet, to any solar system, and don't want to carry along some heavy masses. You just want to go ahead and take your calibrated spring and you just want to grab some rocks on the surface, okay, of that planet X and use those as your variable masses, as your masses. Guess what? I can calculate the mass because the mass doesn't depend on gravity, it only depends on the spring constant. So I can calibrate the masses. So from this, we're on planet X. Okay, you're going to put on a unknown mass. Okay. We're going to take it off slow for a little bit. Okay, the unknown mass. We can start in spring position 4. You can put it at a different spring constant position. Okay. From its equilibrium position. In fact, you might want to put it in there. It's the mystery mass. Okay, maybe you want to, maybe you don't. All right. Maybe you want to put a larger spring constant, maybe you don't. This has a lot of stretch on there. You have a variable spring constant spring, okay? But it's in position 4. Pull it down about, I don't know, 20, 30 centimeters. We'll pull it down just so it's right there at the bottom of the eye. Okay? I'm gonna pause it here. I'm gonna pull it down to here. That's a nice place to find the bottom later, right? I'm going to reset this. I'm going to start it. I'll measure, say, 10 periods. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's slow. Almost 10. Use this guy to move it in 0.01 second increments, which is really cheating. You wouldn't be lucky enough to have that. There's 10. It's already coming up by now. So about 12.32. 32 was 10 cycles. I'm not going to spend a lot of time now filling in those tables. I had 12.32 with 10 cycles. So T is 1.232 seconds. Okay, I had this in position 4. Position 4. 4 implies K equals 6 newtons per meter. Okay, so mass equals 1.232 seconds squared times 6 newtons per meter divided by 4 pi squared. Okay, and that should give you mass of the blue one, or mass 1. Okay, same thing for mass 2. Okay, mass 2 hangs down even further in its equilibrium position. This is no good. That's its equilibrium position. Okay, I can't deal with that. I've got too much. Now, I could cheat and say, well, I'm guessing that my spring is okay out here, so I can go from my equilibrium position, which is right there, and go up about 50 meters. So I pause it, reset it. Okay, I'm going to go up about 50 meters. Right here, I'm at almost, there's my equilibrium line. I'm going to go up here to about there. I'm paused. I'll go to about there. This is my equilibrium line. I've got a movable line I can move. Maybe I'll put it up at the top of here. Find some convenient thing. So I can start at the top just fine. I reset it. I hit play here. Now, first I have to make sure that I start it. I hit play. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Went to slow. I'm going to pause it just before I get to 10. Now move it up. And 15.62, 1.562. So you can do the top side, you can do the bottom side. You could change your spring constant and draw the equilibrium position up higher. This is obviously a heavy mass. Okay, now you know, yes?
Teacher, why the spring constant is 6 Newton per meters? Why
What?
this is Newton per meters?
Because that's the value of spring constants. You
But
did that.
but you have the spring constant in 3. It's not 3 Newtons by meters.
Why was it 6? I had this in position 4.
Mhm.
I had it right there, didn't I?
This one is 4.
This is position 3. This is 1, 2, 3, 4.
Oh, okay.
Now, why is it 6 then?
Yeah, why this is Newton by meters?
Why is it 6 instead of what do you think it should be?
Okay.
What do you think it should be, Anna?
Because I understand what is the constant.
It is. It's a spring constant. I have my spring constant in position 4. What value in terms of Newton meters does that correspond to?
Okay.
Well, no, don't say okay. What I want you to answer. What value does that correspond to? Okay, this position does not mean 0 newtons per meter. It does not mean small newtons per meter. This doesn't mean large newton per meter. This is a position of a slider that is some number of per meter. So how many newtons per meter is it when it's in position 2?
I need to check later because I know
Don't,
this.
don't check
Sorry.
later. You know this right now. You don't get to check later. You know this right now.
Can you move a little because I need to watch the paper. No, the other one.
No,
your
no, you
notes.
asked, Anna, you asked me the question like, what is the spring constant? And this is a really important question, and it's a really valuable question. This is why I'm pushing you hard on this. This is a really valuable question. This is the very first thing we do on the lab. You are calibrating that slider. That is this table. All we know from this slider is it's in a position, okay? This we define as position 1, all the way in small. This is position 10, all the way to the right. Here's position 1. Here's position 2. Here's position 3.
Yeah,
Here's
this is my
position
first
4.
table.
Position 3. Okay, position 2 was 4 newtons per meter. When you get done with this table, you're going to have position 4 be approximately 6.
This
newtons per
needed
meter.
per meters. Oh, thank you. I'm sorry.
No, don't be sorry, because this is what's so important. This is what's not, what is being missed by a lot of students. This is what you have to do with your equipment. Whenever you use equipment, you have to calibrate it. If I gave you a meter stick that didn't have inches on it, that just had some arbitrary thing, I grabbed a piece of paper, or I printed out a piece of paper that I nicely put a bunch of marks on. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And maybe they're even equally spaced. And I give you that piece of paper, and I tell you to go measure the length, the size of, I don't know, let's see what I got a size of. The size of this coin.
Mhm.
Okay, and I want you to measure the size of that coin. Well, it's about 1 division.
Mhm.
Okay, but you needed to calibrate this. This division was, each one of my divisions, well, this division is 3.2 centimeters. This was 3.2 centimeters. This division was 3.3 centimeters. I don't have a very good ruler that I wrote you. This division was 2.9 centimeters. Okay, I have to calibrate this ruler. Okay,
Yes.
you're calibrating the slider here to an actual spring constant. That's really important. That's one of the big things to get out of the lab, is you're calibrating your spring constant.
Okay, thank you.
So I use 6.
Mhm.
Okay, so that's a very good question, actually, and I get passionate about it because that's great when I get that sort of question, because that's exactly what I want. The sort of questions I want is, why do we do this? Then we can circle back to our calibration tables again.
Professor, do we have to use position 4 and the spring constant 6, or is
Here's
it
what
changeable?
you can choose what you want to choose. Just
Got
get
it.
the math right, okay? Because it's not necessarily good. Now, look here, I have here, here you had to use position 4 because you were just validating the formula. Okay, and I asked you to use position 4. But over here, you get to choose your spring constant. I tell you to set it to position 10 because they're heavy masses. And use the calibration table earlier. So it would be 12. You want to use something different, that's okay by me. Okay, but your calculated mass, doesn't matter what you, and prove this to yourself. Doesn't matter which spring constant you use, the mass, you calculate the mass should be the same. Because if you use a different spring constant, you'll get a different period.
Mhm.
Okay, and so, and then for the gravity of planet X, once you have the calculated mass, you can use the displacement method to get gravity. That's the only way you can get the gravity is planet X, because F, you're going to use F, which is equal to mg, is equal to kx. K, you know, X you measure. So this is calibration. Calibration. This you'll measure. Okay. This you determined. This you determined experimentally.
Can you move the lab screens? Thank you.
This was a calibration, K. These were used known masses to get it. X, you're going to measure with your ruler. This we determined experimentally. In the previous part, see, that's the calculated mass based on the period. And now you can write G of planet X is kx over m. You determined the mass using of the mystery object. The spring constant is your calibration. X you're going to measure because you're just going to measure that displacement. So you can do the displacement measure method to measure G then. And that'll give you the gravity of planet X. Using nothing more than a calibrated spring that you took with you to planet X. You didn't even have to take calibrated masses with you to planet X. Okay.
Yeah.
Then we're going to use one with, there's a few questions here. Then we're going to do the damping one. Okay, and how are we going to do the damping? So we're going to go back, we're going to go to our lab icon. We're going to keep it on our lab icon. We're going to use a 100-gram mass on the spring. And I would suggest you just do a 100-gram mass on the spring. Okay, so I have a 100-gram mass on it. We're going to slide the spring constant to position 2. That's right here. Relatively small spring constant. And reuse our calibration table. And 2 was, I think, 4 newtons per meter. We're going to set our damping 1 position to the right. Okay. Now, there's a half a position and there's 1 position. Okay. So right now I'm going to just put it this full 1 position. Okay. We could say that that was 1, 2, 3, 4, 5, 6. So we'll just leave, we'll put it at just a little bit of damping there. Move the mass to the bottom of the mass at the height equals 0 mark. Pause this. Pause everything. Okay, now this, we're gonna move, we have it paused. We're gonna reset it. And we're gonna move it here. The height equals 0 mark. Okay. So we have an equilibrium position. Let me reset everything here. I'm gonna reset everything. Here's our equilibrium position. Now you need to decide where you want to move, what line to what. Okay, because we need to take a look at what our displacement is. Okay, this was the displacement from the natural length. So the green one's not the best one to use. Now we could put this right here as a reference point and watch our arrow as it goes up and down. We can put the center of the reference point right here. We can choose to try to not move this ruler again and put this right here. And then we'll measure the displacement, but we need to measure how this changes. So we're going to start with, we're going to pause it. We're going to start it at the height equal to 0 mark. Okay, so it's at a height equal to 0 mark. And we're going to go one position to the right. Start the timer. It's not going to count until we start the simulation going. We're going to go in slow mode only. And you're going to pause it at times. So we finally got that to switch to slow. Start the simulation and pause it as close as you can to when the mass reaches the top of the first half cycle. So one cycle's up and back. Half cycle is up and down, is just up. The top of the first half cycle. Measure and record the amplitude and time. Okay, so we've got this started. We're moving slow. Okay, we know that it's going to, let's go ahead and set my ruler at 50. Okay, my center is a little bit before, is a little bit after 90. So on this side, it's going to be a little bit after 10, or maybe before, because we have damping. And we're going to put on the period trace. So I'm going to hit go. I'm going to stop it fairly soon. Okay, I'm looking at here, and I see that I'm losing elastic potential. And I've got E thermal going up fast. Now, when we're looking, I'm looking at my gravitational potential, my elastic potential, and my kinetic energy. I know at the end of a cycle, my kinetic energy is going to be 0. So I'm going to look at my kinetic energy bar. I'm going to go in little steps, 0.01 seconds. And down a little more, little more, little more, little more, little more. And I'm basically at 0 kinetic energy now. So I'm going to step forward for 0 kinetic energy. So my first one is at t equal to 0.5 seconds. And my amplitude, my x of t equal to 0.5 seconds. Okay. And we have to decide which way is plus or minus. Okay, but I'm going to just use my magnitude of x. So look at my magnitude. And I have to decide where I was measuring from. I had center to center, and I read across here, and I'm going to say that that was 10, 20, 30, 40, about 42. So I'm going to write it's at about 42 centimeters. Okay, is its amplitude. Now its initial height, we put the bottom here, but I put this at the center. Okay, so that's a little bit funny. I've got about 6. And I should have recorded what it was at 0, which I didn't. Okay, and we need to decide whether we're going to use top, bottom, what we're going to use as our reference point. And I'm going to leave you to decide that a little bit. But I'm going to start this over because I'm not happy. Okay, so I'm going to pull this back down. Right here. Okay. I'm going to look at, actually what I want to do is I want to play it. I want to reset it to the center. Okay, and pause it. Okay, so I am putting my line, my red line is at the bottom. So I'm doing everything from the red line is at the bottom. So x of 0 and you're going to have to estimate on the other side, x of 0 to the bottom, that's my reference point, the bottom is 48 centimeters. So t equal to 0, x of t equal to 0, magnitude of that is equal to 48 centimeters. X of t equal to half, which is again watching the kinetic energy, x of t equal to 0.5 seconds. And I'm going to go from here to the bottom. So it's 50. So here we had 48. It's going to be 10, 20, 30, 35. Now we're going to go x of t equal, well, I'm not sure what that's going to be yet. Again, we're going to watch the kinetic energy plot here. Up, coming back down, pause it, step forward till it goes to the bottom. And that's going to be at 1.00 seconds. And it is, the bottom is going to be 10, 20, looks like about 27 centimeters. Now, if you find that there's too much damping for that mass, go to a higher mass. Change your spring constant versus your damping. what you want to do is leave the stamping in this position. Your job is to calculate the damping factor. Okay. Now I'm going to go some more. Again, watch your kinetic energy curve. Up, coming back down. Now you might guess it's going to be at about 1.5 seconds. And the bottom is now 10, looks like about 19. Or 9 centimeters. X of this is a little time consuming. I'll give you that. Almost down to the bottom again. And that's about 15 centimeters. Okay, now I'm going to do one more. And sometimes we have this trace to come across nicely like this. And I'm going to say 11 centimeters. Okay, now I'm just going to do those 5. You have to do more of them. You can choose 12 half cycles and you can set these up for else. Okay, this shows. Okay, now I'm going to back up. I'm going to have you guys do it at a little less damping factor. One position is going to be halfway between these two. I drew in some pictures here. So do it halfway so your amplitude isn't so bad. So again, let's just start this over. Okay, X is 0, still 48. I go up to the top. Still 50 seconds, but I would say it's 40 centimeters now. So I'm going to put 40. I want to do these so that we're at the same thing. Now I'm going to go to the other side. Now I've got 10, 20, 36. Up to the other side. Call it 30. To the other side. Call it 27. Up to the other side. Now you're going to do them all. A note, you see this comes across. So now this is 10, 20, 1, 2, 3. Call it 23. Okay, so I've filled in some of these. So x0 is equal to a. At t equals 0, x equals a. Okay? Because it's 40 centimeters. So we're going to label a equal to 40 centimeters. A equals 40 centimeters. 40. So at t equal to 0, so at t, we have t, we have x over a, and we have ln of x over a. So I have 0, I have 40, I have 1, then I will calculate ln of x over of 1 in a moment, but it should be 0. Then at 0.5, we have, oh no, sorry, this was 48. At 0.5, we had 40. X over a is 40 over 48. At 1.0, we had 36. 36 over 48. At 1.5, we had 30. 30 over 48. And these numbers don't seem like they're right. Remember, don't trust my numbers. Do your own numbers. 2 is 27. 27 over 48. Okay. Now, when we take the natural log of these values, okay, let's look at what the natural log is. Well, 1 ln, that's 0. 40 over 48. That's minus 0.182. 36 over 48. Take the natural log. Minus 0.2877. 30 over 48. Now this number is suspicious. Take the natural log. Minus 0.47. I'm very suspicious of this number. 27. Take the natural log. Minus 0.575. Okay, so I've got a batch of numbers here. Okay, that would be, you're just going to do this on your calculator. You're going to plot displacement versus time. And in your first plot for displacement versus time, you're going to get a curve that comes down like this. This is the maximum displacement. So this is the maximum displacement versus time. You're going to have a curve that's going to come down like this. Okay, and it's going to start at, say in my case was 48, and eventually it's going to head towards 0. Right down here is 0. Okay. Now, the maximum displacement is when this term here equals 1. So, x max is equal to a e to the minus b over 2m times t. Or we can write X max. So that's going to be its max displacement at each cycle, each half cycle. That's the value you're getting in this column here. Okay. This is one of your more difficult ones in terms of understanding what you're doing for the purposes of the lab. Up to last. Okay, that was our X max at each cycle. So each cycle. Okay, so X max over A equals E to the minus B over 2M T. So X max, remember, X max is equal to displacement at end of half cycles, or when cosine omega t plus phi would equal 1. So that's always at the edge of the displacement. Okay, so we're setting X at those times. So our times are the 0, what I just measured is 0.5, the 1, all of those things. So X over A is equal to E to the minus B 2M over T. But a neat fact is the fact of logs. So the natural log of X max over A is equal to the natural log. I'm just doing the same thing to both sides, E to the minus B over 2M times D. But the natural log of E of any value to the X, properties of logs, that's going to equal to minus B over 2M times T times the natural log of E. I just took down what's in front and I have natural log of E. But the natural log of E is equal to 1. So E, the value of E is 2.713. I take the natural log, it's equal to 1. Natural log of E equals 1. And again, properties of logs is log of A to the X is equal to X times log of A. That's the property of logs. And you have seen logs, earthquake scales talk about logs. The difference between a earthquake of magnitude 1 and an earthquake of magnitude 2 is 10 times. The difference between a 6 and a 7 is 10 times. Okay, they're very valuable when we have very nonlinear processes. Okay, so log of E equals 1. So I can do ln of X max over A, or what we measured of X over A. Remember we measured X over A. We measured X each time at the edge of the cycle. We have A, that's the initial displacement. We take the natural log of all those values. That's what I was showing when I did say this here. You're going to do your own tables. That equals minus B over 2M times T. Okay, so I've got a plot of this. It's a nice straight line. you guys were taking the log, it's a nice straight line. This is the slope. So when you plot the values for your natural log of x over a, you're going to get a straight line coming down this way from 0 at 0, coming down negative. And that's going to be its slope. Since you know the slope, you can calculate b minus b over 2m is the slope. That's the slope of this straight line. You've done slopes before. That's rise over run. Okay, and that's going to be equal minus b over 2m. You're going to get a negative slope there. So now you can calculate b, because you know m. So you're gonna plot your data, determine the slope. That slope is going to have the rise over run, and that's going to equal this minus b over 2m. So the point here on this lab is to show you how to take a look at your data and look at the data and say, this is a pain to process, just displacement versus time. But the log of the displacement versus time isn't so hard to process. Now it turns out, if you do this with, things like Excel, they'll do that all in the background for you. And they'll give you the damping factor and things like that. Okay. And you can also fit a straight line in Excel and all of that good stuff. I'm just seeing if I have a particular set of data here. So for instance, here's a batch of data I did. Here were my values of x at 0. Here's my values at the different positions. So your table is going to look something like this. I did this at spring constant 4, presumably. Hope that's right. Okay. So I had a spring constant of 4. Here is, if I just do the exponential and fit that line, here's my nice straight line. So this is like my plot of ln of x over a, and here's just my plot of x. So here's a plot of x versus time. And here's a plot of ln of x over a versus time. I did this with a spring, and I did when I was doing this data here. This was position 2, which is spring constant 4, using 100-gram mass. Okay. So minus 2.84 is the slope I calculate here. So for instance, I did a minus 0.284. It equals minus b over 2m. So b equals minus 0.284. So plus, I'll get a minus sign and minus sign gotten rid of, times 2 times the mass. Okay, so you're going to calculate that slope, but that slope is minus b over 2m. A little bit more than we've done before. All right. But not so much so. And, you know, it's a good piece of data, a good lab to understand analyzing data. And doing this analysis of data is very important. I don't know what fields, you know, many of you might go into, okay, but we're doing physics for, you know, science in this class, science majors. You're going into medical fields. And you give, say, medications. There's a thing that is often referred to as medications that are referred to as biological half-life, okay? Which is different than, say, a radiological half-life. It's a biological half-life. How long does it take for that substance to get into your blood or out of your blood? How you know, anything you take in gets distilled through your kidneys, it gets into your blood system, your kidneys, your liver, everything distills things. There's things referred to as a biological half-life. All right, you go into that, you say, okay, how often should I give this drug? For example, I know some people on blood thinners that they need to help keep them from having a stroke. It's actually more dangerous if they forget to take their pill than if they weren't taking it at all, because it's messing up, because it has a biological half-life of about 8 hours. You really want to take this stuff at about 12-hour increments to get the steadiest state level. So you're putting some in, and you're putting a bunch in, it causes a spike. You have a biological half-life, but that came down some, but it's not all gone because it takes 2 half-lives to be gone with 3/4 of it. Okay, you're not, 2 half-lives doesn't get rid of it all. It only gets rid of 3/4 because there's a log progression in it. You lose a half of it every half-life. Like you hear about radioactive decay. If I have a kilogram of material that, say, is decaying, and it decays by half in a day, then in a day, I'm going to have half a kilogram. But in another day, it's not all going to be gone. I'm going to be down to 1/4 of a kilogram. And another day, I'm going to be down to 1/8 of a kilogram. And another day, I'm going to be down to 1/16 of a kilogram. Same thing when you do biological half-lives and medicines in your body. It comes down at an exponential decay curve, but then you put some in, and eventually you get to a nice balancing act between its decay and you putting more in. And they come to a nice, relatively steady state during that period between doses. You miss doses, you've all of a sudden mucked up the interval again. Same thing for other sort of chemical treatments of the body. Antibiotics, and how often you should take the antibiotics if you're taking steroids. So a lot of things in medicine that are very important in this. If you're going to do the research in the chemistry, biochemistry, you know, engineering, you need to understand the analysis of data. You're going to take data like this, you need to take a look at it, and you are often going to find that you're going to work with logarithms to analyze your data to get nice slopes. They become very nice fitting parameters, and we like to fit to logarithmic scales. Many things in nature follow logarithmic scales and exponential decay factors. So hopefully you find a little motivation out of this, even though you might find it a little bit troublesome. I'm hoping that you find some motivation out of it. All right, and that leaves us done for the day.
Okay, thank you, teacher.
Okay,
Bye.
good
See
rest
you.
of the day.
I
Thank
have a
you.
good one.
I know.